Good morning, everyone. Today is July 6th, 2019, and this is the John Chappell Natural Philosophy Society Science Chat. I am your host, Franklin Hu, and I am just fresh back from the John Chappell Natural Philosophy Society 2019 conference. So every year we publish a proceedings, which has most of the papers from the speakers. And I believe you can order this from lulu.com or something. That's where we get our proceedings from. Let's see here. Now, Avercheck, he wants to discuss a link here. Well, I guess we could start with that. Let me see if I can click on that and see what he's looking at here. See, he is looking at slow motion and the eventual disposition of black holes. Okay, now let's share that. So what does this say here? Well, this is a pretty long article, it would appear. Let's see if we can get the gist of this. Well, this is about black holes. And this is something from Avercheck. So this is a blog. So he writes, solids, unlike gases, are in the atmosphere. Let's see. So Avercheck is here today. Let's see where. Okay, I'm going to unmute you. So Avercheck, would you like to lead the discussion on this article? Can you hear me? Hello? Avercheck, can you reply on your microphone? Well, it'll be a little bit hard to have a discussion if we can't hear you speak. Currently, we cannot hear you. So let's just go over your article here. So this seems to be a conversation between you and somebody else here. Let's just read what it's saying here. This is about degrees of freedom, and that there is a gas that have fewer degrees of freedom. But this would mean that there can be matter without motion, because the degrees of freedom of any form of matter becomes zero. It would not be in motion, and it would be a form of matter without motion. Can you please deeply look into this? Well, I don't really understand that myself. I would certainly think that there can be matter without motion, and I don't see a problem with that. So that would be my answer. It says, yeah, if it becomes 0 degrees Kelvin, it does matter without motion, and that's it. But what is, who is GB? GB is saying that it is a violation of the fourth assumption of inseparability. And all things must be in motion because there's really no way to get down to 0 Kelvin. So generally speaking, that situation would really never practically exist. This is the answer by Glenn Borchardt. And you've got fusion, continually making things here. But do they have 0 degrees of freedom? So now he's talking about black holes. And that they're so dense that they would have 0 degrees of freedom. Now, personally, I think that degrees of freedom doesn't have to do with actual motion, but potentially where it could move to. So even something at 0 Kelvin, I would say, has the opportunity to move someplace else. So it would still have the 3-dimensional axis of motion. But now he's getting to black holes here. And average, if you can get onto the chat, we can probably you can probably write something in there. And this is something about the formation of baryonic matter. And then that's it. So that was a bit of a ramble, I would have to say. So that's Aberchecki asking a question, and then Glenn Borchardt providing this reply here about 0 Kelvin. System here. I think that might have been Abercheck himself. He does not seem to be able to lead our discussion here on this. But he got a nice reply from Glenn Borchardt to his question about 0 Kelvin here. Like I said, I don't believe this statement here that gases have fewer degrees of freedom. I really wouldn't know what that would mean. I would think a gas has every degree of freedom possible. Oh, they're saying that solids have fewer degrees of freedom. Okay. Well, only in the sense that they are typically locked into their neighbors. I suppose could agree with that. But I'm not sure I terribly understand the nature of this relationship between 0 Kelvin, and especially the relationship between black holes. So does anyone else have any comments about this article? I just tried to go through it as I was reading it. All right, well, let's see here. Let's move along then here. So I see Abercheck, I can see your chat there. Did you have any comments? I just tried to give you my take on that questions and answers there. But if not, then as I said, we can move on. I was going to review what was going on in the CNPS conference this last week. And as I said, we published the proceedings for the conference every year, and I believe you can order this from lulu.com. And but let's go over it. So the conference, that was 1, 2, 3, so 4 days, and each day we would have a speaker, and I'll just generally go over the topics that were there. And if you guys have any questions about the topic, then please feel free to ask a question, and we'll see whether I can give you a comment on that. All right. You guys are out there, right? All right. So far, I haven't heard a peep from anybody. So let me know that you guys can hear me. So someone say, yes, Franklin, we can hear you.
Yes, Franklin, we can hear you.
All right. Thanks, Carl. Okay. Thanks for that. All right. So the conference started out, and we have an article by Musa. And Musa's an interesting guy. He comes all the way from Africa to come to our conferences, and normally he comes every year. So he would get the award for the person who travels the furthest for our conference here. So his paper was on the electric field model of the ether. So he basically, I mean, this is very much like Bill Lucas's conception of the ether, which is that the electric field itself is forming the ether. So let's see. So how does he do that? So he's saying that there's matter, and that all matter consists of positive and electric charges, and that that those things put out the electromagnetic field, which crisscrosses everywhere, and therefore that becomes the ether itself. So he has a number of equations in here to try and justify that. And let's see, what is his results and discussion? So the paper has succeeded in presenting ether as a balanced electric field medium, which has pressure, energy density, and mass density. So one of the questions I was asking was, if it has mass density, then what is the density? So I think that was basically answered in terms of, if you converted the energy that's omnipresent in the field, then you could get a mass out of that through the E equals mc squared kind of equation. And he's saying that it accounts for the force of gravity between bodies in space, which was equation 16. So he has a very complicated equation for gravity. Force of gravity equals what appears to be the normal gravity equation but that's kind of accounting for the force of gravity by using the force of gravity. So I'm not terribly convinced about that. And let's see here. And this pressure, like atmosphere pressure being uniform in all directions at a point, is not perceived except in isolated or abnormal circumstances. So the ether exists as a manifestation of electric fields from electric charges in matter or from bodies in the universal space. Electric field model of the ether is simpler and more useful than the particulate models under discussion by physicists. The electric field model of the ether should put to rest the notion of warping four-dimensional space-time continuum to make for force of gravity between objects. So like I said, this is probably similar to what Bill would promote as an ether. So maybe that would be something you might want to take a look at. Personally, I don't like making the electric field fundamental, and I would probably once again be a person who would be advocating for an actual physical ether, and then saying that the effects that we see in the in the way of, say, charges and things like that are manifest as a result of that. But people can choose to start where they like, and it is possible to indicate that the thing that fills all of space is the thing that we measure, which is the electric fields and the magnetic fields and the gravitational fields. So I wonder, Bill, do you have any comments on that? I think that one was right down your alley. So.
Well, one comment might be that um, which is first, the chicken or the egg? Is the particle first or is the field first? And that's the question that we have different answers for. And
Yeah, what is first? Yeah, we have these things, we have particles, we certainly know that we have that, and we certainly know that we have electric fields. Now, me personally, I think I think the chicken came first. So,
well,
but I
what is
would,
the chicken? Is it the field or is it the Winston Bostic in his experiments was able to make from just the disturbing the field, he was able to make solitons, and from those solitons, he could make an electron. And so the question is, uh, can you do it the other way around? Can you make a field from an electron with no field? And that doesn't seem to be possible. So logically, it looks like the evidence is in favor of the field being first and the particle becoming field structures. But we all have our own ideas, and the role of logic in science has been removed for the last uh, 50, 70 years. So,
well, I guess the question would be, what was Winston Bostic actually doing? Because he was working with like plasma fields, well, or at least plasmas to create his
yeah,
solitons. Now, while he may have created solitons from plasma, I would question whether that has anything to do with creating electrons out of the electric field. I would consider a legitimate experiment would be if you were to create, say, an extremely strong electric field between, I don't know, like two plates or something, and then showed the spontaneous generation of an electron, which could be detected in whatever way. So that would be a direct experiment showing that you could create electrons out of basically empty space. Although the problem with that is that's kind of a production of charge thing. And if you were only to produce an electron, per se, then that would be an unbalanced charge. It would have to be a production of at least a positron and an electron. Now, I suppose the closest experiment we have to that is the pair production experiment, whereas you send a gamma ray, a strong enough gamma ray, into empty space, except for there has to be a nearby massive atom. You do see the production of the electron and a positron in those cases. Now, that doesn't have anything to do with solitons and has nothing to do with the work of Winston Bostic, but it is one of the probably the only experiment that we have that's showing the production of material particles, starting from what we would consider electromagnetic energy, which is gamma ray, right? So we really only have that work with. So, like I said, my comment about whether an electron can be created from the electromagnetic field is still, especially from the work that Winston Bostic was doing, and what he was doing was interesting, but basically it has nothing to do with actual electromagnetic fields and actual electrons. I suppose it helps motivate, providing an analogy for how that might happen. You can blow smoke rings and say those are particles, but does that really have anything to do? I mean, that might motivate the physical way that the particle might be formed if it was a tori, but it may actually, in fact, have nothing to do with actual experiments around creating electrons. So that would kind of be my comment. And now I would say that can you do the opposite? Can you create the electromagnetic field starting from just particles? And I would argue that, once again, experimentally, we don't have much to go on. But if the electromagnetic field is considered to be the medium for the electromagnetic electromagnetic waves, then a sea of any kind of particle would probably serve to be the medium for that wave, if it's just like an ordinary compression wave. So in that way, I would say that, yeah, particles can represent that wave, or at least the field. And you'd have to represent things like the electric fields also as waves. Because really, there wouldn't be much else to represent them. If you have a medium, there's just only so many things you can do with it. And mostly, you can put waves into it. So that could easily account for light, right? So I was kind of curious. So, Bill, what do you think of the alternative? So, one alternative is that the electric field is fundamental, like Moose is saying here. Or the other possibility is that the particle is fundamental and it fills everything. Those are the two things. Either ether is made out of particulate stuff, or the particles are made out of something. Well, I don't think Nusa actually even says what the particles are made of. Nusa just says that those exist. I don't think he says anything about the particles being made out of anything. So I guess that might be different.
There's a logical problem that has to be resolved, and that is the fields where properties of electric and magnetic fields were measured. And I think I've talked about there were 13 properties of them. And the one property that all the fields have is that the fields are continuous and they're not composed of individual particles. The fields are continuous and they have tensile strength. And so the question is, how can we have a particle that is separate from the field and being the source of the field? How can we have that with the field being continuous and having tensile strength? And so what the experiments say is that if you have an electron and you're going to assign the field to it, then the field is infinite. So that every electron has an infinite field. And then, of course, that means that all electrons at all distances in the universe are interacting with one another. But if you're going to have something called a particle, then the continuity of the field and the tensile strength of the field should be different as I get near the particle. And in fact, the question is, it looks like from logic you can't have the particles being the source of the field. It looks like the only way you can satisfy the experiments that have been measured is to have the field having excited states that are particles.
Well, I don't think that anyone would say that the field is. Let's see here. How do I say this? That the fields are mediated by the particles, right? That would be the hierarchy. It would be incorrect to say the fields are made up of the particles. That wouldn't make any sense. But what do you think of just the analogy that we do know how, say, the air and sound waves work, right? So to try and answer your question about, what does the electron doing? Now that could just be emitting something like a sound wave, and that wave could in fact travel infinitely far if the medium is frictionless. So the kind of space I typically envision would be like a superfluid, frictionless superfluid consisting of some particles. So, listening to the things that you asked, it's like, I would say that I would be able to answer most of those questions, assuming, though, that the field itself would have to be some sort of wave. So an electron would be waving, the electric field that's measured around it would in fact be just like measuring the intensity of a light from a light bulb. And that the fields that so that's one way to measure the field that we discussed in my talk, exactly what do you mean by a field. And one of the things about a field is that you can measure at every point in space. We have electric meters, we have magnetic meters, and you can put them at any point in space and come up with a different measurement. And basically, but that's basically what we have to explain. Why does that have a different value in space, right? So,
one of the problems you're going to have is they found there are 3 types of electric fields and 3 types of magnetic field, and so you need to be able to explain how an electron, a particle, can generate 6 types of fields, and each of them has
once again, we'd have to go take a look at those experiments and see. I mean, I know that from reading that, I don't know that he's saying that there are 6 distinct types of electric field, because I think we can clearly distinguish between magnetic and electric fields. Those 2 things are different. Now,
right.
Between
there are electric fields that can be shielded and electric fields that cannot be shielded.
Yes, but for example, that is one good example of that. There are electric fields that can be shielded and electric fields which cannot be shielded, but I think technically those are both electric fields. So in that way, that's kind of like different reactions that you can get from the electric field, but the electric field itself could still be the same thing. But you'd have to explain that when you have like an electric charge that's just sitting there and it's putting out its field, that it cannot get through, like, say, a sheet of metal. Okay, versus an electric field, which is just moving around, it's creating this variable electric field, but that can get through the metal shield, right? So you have to explain things like that.
And also,
but, that would be
the electric magnetic fields have chiral symmetry. So how can a particle make something with chiral symmetry, which has certain types of properties, so I guess that's another issue that you can raise. And also, why does when you make your different elementary particles out of something, either electrons or positrons or something smaller in terms of a particle, why are there only certain symmetries in the structure of elementary particles? Why aren't there more variety? And you would think that if particles were the source of the fields, that things would be more spherical around the particle, but they have chiral symmetry, which is not spherical. And,
hey, Bill,
yes.
Gray here. I really need, and hope you can provide me, either now or offline, references to the 3 different kinds of electric fields, 3 different kinds of magnetic field. There was one researcher, the name I forget at the moment, he had a book out, I think you were editing, that came up with some of that. But are there additional experimental references? Because I really need to understand that from the experimental point of view, and I haven't been able to understand this other guy's book well enough to really clearly understand the experiments that he was doing to determine that there are 3 different electric fields, 3 different magnetic fields. Any other references?
Well, the book is the best. You can get copies of the book for free on the internet, but the diagrams are not perfect. But I mean, they were messed up by the person who was copying them. They couldn't get hold of they got hold of a Xerox of a Xerox of a Xerox. And when you keep making them that way, the images sometimes fail to be perfect. And
Bill, if you can find like an internet reference, you can put that in the chat, and then maybe Bob can get it from there.
Okay.
Oh, I know. It was Bill Hooper, right? Yeah, I have Hooper. Bill Hooper's book.
Yeah, William Hooper, I think. And he was interested in the relationship between gravity and electrodynamics, because from the experiments he was doing, you can do the same experiments on gravity, and he was able to show experimentally that gravity is only due to one type of electric field, and that is the one type of electric field that cannot be shielded, and gravity, of course, cannot be shielded, and yeah, I should. I think I can publish that book now, so you can have a nice copy of it. And I'm going to probably put it on Kindle. So that
did anyone else pick up on William Hooper's work and carry it on or reproduce it? I'm thinking maybe Thomas Barnes or somebody else like that has gone and verified the experiments, repeated the experiments?
The experiments were repeated at University of California at Berkeley, and that's where also they were originally performed there. So it had to pass muster through that university as a valid experiment, and it did pass muster, but the ramifications are hard to accept, because it falsifies the theory of electrodynamics that is currently being taught. Now, it doesn't falsify the work of Maxwell. It falsifies the work of Oliver Heaviside and his followers. And so that is the one of the important aspects of it. I've been working a long time trying to do that, but I have a lot of other people that you have probably never heard of before, like Joseph Barreto from Spain, Madrid, Spain, and he has been working on a theory of elementary particles based on this notion of the field being the source of the particles, and I helped him publish some of his work, and he was working at the time I was working with him at the Fermi National Accelerator Laboratory with Fermi, and Fermi was very interested in his work, and but unfortunately Fermi died while they were just getting started on it. But he had invited Barreto to come from Spain to the University of Chicago and the Fermi National Accelerator Lab to work on these types of experiments.
Okay.
So yeah, there are a number of papers out there, but you have to know some of the key words in order to find them.
Yeah, so if you could find some references, and then we could take a look at that. But going on with the other, so Musa had another paper here, and this was about the aberration of the electric field and about the accelerated motion of an electron. Now, the aberration effect is, typically thought of as something that happens when you're observing a star, but Musa was saying that as you're observing a moving electron, that somehow you get a similar effect. Now, I think the main conclusion he was trying to make here is that because the electron is moving, has this aberration effect, that effectively that electron can orbit without radiating, was his thought there, due to this aberration effect.
Well, the problem with that is, in electrodynamics, if you have a particle is not continuous at all distances in normal electrodynamics and normal quantum mechanics. And so what happens is, if you don't want to radiate, you must have a continuous blob of material. So in the case of the work I do, it's a continuous toroidal ring for the soliton. And but if you don't have a continuous ring, then you have to radiate. And we cannot. The only way we can make a continuous ring in the laboratory with an accelerator, we can't take individual electrons and use a cyclotron and make a continuous ring, because there's a separation between the charges. The charges.
Yeah, so I guess that was the point of his paper, though. He was saying that you could get around that rule by looking at the aberration of the force, I guess. I'm not sure I quite understand that, but that was kind of the main point here.
No, the fundamental empirical laws of electrodynamics, called Maxwell's equation, they require that whenever a particle is accelerated, if it's a particle is the concept that it has boundaries, and so the boundaries are on the charge, and then the field is maybe not affected the same way, but the charge is. And what they have in the case of the soliton and things that don't radiate is they have a continuous charge. Even a wire in a circuit, if you run current through it, will radiate. The current going around the line. And so it looks like the only type of structure that we've found so far in science is the soliton, which is continuous. It doesn't have, it's not composed of particles. And so anyway, that's the one of the issues that has to be
all I can do is we've got these equations here, like he says there's equation 19 over there, somehow says that the radiation power is 0. So I don't know if that's true or not, but it has something to do with aberration. So my only comment on this is that I feel that the Rutherford model itself is not correct. So if the electron doesn't have to orbit around the proton per se, then we don't have a radiation problem. So if we have the hydrogen and proton and the electron, and all it's doing is just the electron is just stuck to the proton, then we would expect that would not radiate. So I would say that I'm not sure whether this whole aberration thing has anything to work, but I don't think it necessarily needs to work. Because it just doesn't really make a whole lot of sense for electrons to be flying around the atom anyways.
Well, all of the theories of the atom, where the electron is some kind of particle that orbits around the nucleus, all of them only predict half of the emitted spectral lines from an atom. And
yes, but they do still predict a fair number of them, so they can't be completely off.
The best the direct one predicts 50%, exactly 50% of the spectral lines. And NASA measured those spectral lines for a number of atoms, and they did it in space so they could see the extreme ultraviolet. There are no extreme ultraviolet spectral lines by any theory of the atom, as far as I know, except for the one that my son used for his science fair project, which
I think
the grand prize at the International Science Fair.
And I would be in agreement with you and your son that I don't think that the electrons are orbiting, but based looking at the formulas produced, they seem to be forms but they're basically combinations of basically Coulomb-Loss forces. It has to do with the electron just transiting certain distances away. And so I feel that things like the spectral lines are produced by the electrons actually just moving up and down the various distances away from the atom. And so any kind of combination of Coulomb's law describing the differences between the various available levels is what we're going to get for spectra. It doesn't have anything to do with anything orbiting, really. I don't think it ever did. Because none of that is actually based on anything orbiting, really. That was just something that was come up to explain the ionization energies. and things like that. But going on, we had another article from Robert B. Hilster, and he was trying to explain his particle models, where everything is made of this particle he calls G1 or G2. And he's trying to say that the electrons are basically those kinds of particles. So what he did is he's trying to prove his theory by saying that if electricity is these particles, then there would be like an excess when you are going through a resistor. So curiously enough, so he went and bought or rented this really, really super high precision voltmeter, like 6 digits of precision, because you need that in order to detect what he was predicting as a slight difference in a voltage drop. So he has this simple diagram of a battery with 3 resistors, and he made some predictions saying that if his G1 model is correct, then he would have some difference that would be not predicted by the normal Coulomb's law. Coulomb's law. So he's looking for a difference between, I say, Coulomb's law and whatever he measured personally around this particular thing. So, and I guess he says he's got something like a 73% correlation with his experiment. But that would basically be his basis of his experiments, saying that basically, what does he have here? It's like the number of particles. He's trying to measure, say, the number of particles that would have to be flowing through at any moment. And he also did that with explaining parallel resistors. And he did another physical experiment around that as well. So he has diagrams that look like that. But that was, once again, his ideas that he was trying to get across. But that's interesting. He actually does a physical experiment. And I'm not too familiar with the details, but I always admire anyone who's willing to do a physical experiment, particularly when you use, like, this is not an experiment you can do with your standard meter you get from Radio Shack. You have to use these high precision voltmeters that are good down to six digits of precision in order to see anything. But I'm not sure whether what he got was really significantly different than what one would expect. It kind of looked a little bit like he was just trying to re-explain the existing laws. But I'm not exactly sure what it had to do with how his particles work with the number of particles that were flowing through. So that's Bob. So Bob's an interesting guy. He's like 80 plus years old, and he comes to the meetings with his son David, who's basically our leader in the CNPS. Now David himself also had some papers, and one of them that he talked about was about the 400 years of model revolution. So he thinks that there's this cycle that science goes through. That this is called the Kuhn cycle here. And he thinks that we are currently in a situation, we are in a model revolution, that there are a bunch of things that we just can't explain. And so everyone is coming out with what their explanation of things might be. So I suppose that we're kind of in a model crisis because we have things like black energy and black matter, which just basically means we don't know what the heck those things are. So the field is ripe to figure those things out. Of course, we here in our science discussion, we're always discussing things that science doesn't know about, like gravity and electric charge and magnetism and what particles are made out of or what fields are made out of. All of those things are probably open discussion. So, but that was kind of the thing that he was trying to get at, that we are in a model revolution, although it kind of feels like we're just kind of stuck, really. That would be my comment. that ever since after Einstein, we have a standard model. Everybody thinks that works wonderfully, except doesn't explain anything. But everyone seems to be, either really happy with themselves or, in the back corner, they're all discussing that, none of this, we've hardly explained anything, and that there is some kind of big problem going on here. So it discusses what's going on with those models and the different kinds of models that, at least here in the CNPS, we've been coming up with. Now, the other thing he was discussing was science evangelism and what we're doing with our YouTube and what we're doing with our woke movement. So one of the main things he was saying was that if you come up with materials on YouTube, that if you come up with something that's very nicely scripted and with beautiful graphics, and if you look at David's videos, they're incredibly have high production values. He's like, they basically have to come up with reading with the script, and he has lots of well-prepared graphics in his things, and he doesn't produce that many of them, but the ones that he produces, you can see that he retains his audience over a long time versus say things like the science chat where we're not scripted, we're just kind of shooting from the hip all the time. And while we might be doing interesting things, it's like basically your audience participation drops from like 100% from the time you stop to like, maybe 10% by the time you're done, versus some video where you'll retain like half your audience all the way through to the end. So I think that was one of his main advices there, that if you can produce something slick, and he showed how you can create like opening logos and how he created logos for various other people, that those kind of things hook the people in and get you to stay. But definitely we are in a different world here where things like YouTube and the internet really allow you to spread your information. Now, I know how difficult these things are to produce, and I personally barely have enough time to spend 2 hours with you guys in science doing our little science chat here. So, and I really should spend some more time watching David's videos, because he really did put a lot of effort into those. But that was one of the things he was talking about. So let's see here. What's going on here? So during the conference, we have a guy called Raymond Gallucci. He also comes a lot to our conferences. Now, the fun thing about Ray is that he doesn't have any particular theories of his own. So what he does is he goes and analyzes, say, other people's theories or other things that other people do. So one of the things he looked at was the intrinsic redshift in quasi-stellar objects, with there being some mass dependence and quantization. So, and this was based on the work of Halt and Arp. Now, Halt and Arp always said that the redshift wasn't due to the objects receding, because you can see these objects which seem to be attached to other galaxies, but appear to have different redshifts. So that's as far as what I heard about this. But the new bit of information was that the distances that these objects appear away from their host galaxies is apparently quantized, that they only appear at certain distances, and that their mass, their apparent measured mass, is also apparently quantized, that these stellar objects only appear at certain masses. So that was news to me. But I think, let's see here, I think he noted that, but I'm not sure that he was able to come up with something that would explain why there would be such quantization. But I think he analyzed to see whether there did appear to be a quantization. And I think he said that that there was a quantization to be found. So he had a bunch of graphs and charts and such. Now, I'm not exactly sure that I understand what all of these graphs and charts and quantizations mean, but it is an interesting fact that these things might be quantized. Let's see. So his summary is, I have attempted to tackle the topic of quantization of intrinsic QSO redshifts, especially based on the lifetime work of Halton Arp, examining first the potential relationship between intrinsic QSO redshift and QSO mass, then the phenomenon of quantization for both QSO mass and redshift. My approach has been primarily a mathematical one, as developing a theory for intrinsic QSO redshift, let alone its quantization, is beyond my expertise. Based on my mathematical analyses for QSO mass versus redshift, I postulate a geometric explanation of intrinsic redshift given a possible dependence on mass to the 2/3 powers related to possible attenuation of light energy and therefore frequency within the emitting nucleus of a QSO, compounded by further dilution and therefore energy and frequency decrease due to spread over the surface area. So I guess that's another thing we can add to our quantization mysteries. We already have like Bode's law, where the planets are basically spaced such that the next one is twice as far than the previous one. And so we have quantization of these stellar objects, right? But it's kind of it's a little bit iffy because, you know, I could understand the work of Halton Arp where there's something clearly connecting these stellar objects to their host galaxy. I think in this case, they're just thinking that these are these stellar objects. What are they? They're like neutrino stars or something. But he didn't say that specifically. But there's some specific kind of star. And that these are not specifically attached to their parent galaxy by anything. So this could be a case of cherry picking. That they're just saying that these objects are found in a certain particular orientation to their host galaxy, and that the chance of them just being there is fairly small. So, but it's not as clear as there being like something physically connecting the two objects together. Would be my comment on that. Okay, so next, Ray worked on the plausibility of Earth once having a thick atmosphere by examining the rate of impact cratering. So I think he was trying to figure out, based on the cratering, so what you do is you look at the moon, which we know has never had an atmosphere, and you look at the rate of cratering there, and then you look at the rate of cratering on the Earth, and you try and see whether, I think if like it was a thick atmosphere, it would have blocked out some percentage of the impacts, is a theory, right? So he's trying to find some correlation, I guess, showing a difference between the Earth and the moon. Of course, my question was, how can you tell what the impact rate of the moon is, right? So I looked at that, and it turns out that when we sent astronauts to the moon and they collected all that rock up there in the moon, they think that they can date any surface of the moon. And then it'd have to be a little bit more speculative about, based on where they collected things and how that looks like, they can get a basic chart of the previous lunar bombardment rate or something. So there's a chart there. So not exactly sure if I understand that or think that they could possibly do that, but so they can make some kind of prediction. And then they go around the Earth and they make a survey of all the impact craters around the Earth. And I would think that it would probably be easier to figure out the dates of those things. But I think he compiles all this data and he comes up with some charts here, and he has to compensate for certain factors, such as we know more about the cratering in North America because there's just more people looking, and so that might have affected the perceived rate of impact cratering just because we found more in North America. So he had to either exclude or include that. He did both, but just to compare. And let's see here. What did he finally conclude? That the cratering rate analysis does not contradict the postulate that Earth's atmosphere has varied substantially in thickness as per Esker, and offers an independent means to test a hypothesis to supplement the more biological and aerodynamic ones that both he and Leventhal provide. So that's one of those things that does not contradict, I suppose, but perhaps doesn't completely confirm either. I think he's just saying that this is a possible avenue to get some more data from. Although, like I said, my comment in this was that I think would be incredible if you could go back and get any idea of what the cratering rate has been for the past couple billion years when this might have happened. But this also brought up the possibility that the reasons why the dinosaurs were so big is that the atmosphere was in fact so thick that buoyancy effects would have allowed the creation of much larger dinosaurs. Now, some people were bringing up the expanding Earth hypothesis, but that was not part of his analysis. His analysis presumed a constant radius Earth, and that the dinosaurs were immersed in something like maybe 30 or 40 times current atmosphere. So it's so dense that it would be like floating in water, basically. So very much larger creatures, like the whale is the biggest creature currently on the Earth, bigger than any dinosaur, and that the dinosaurs were allowed to get bigger just because of this incredibly thick atmosphere that may have existed. And that incredibly thick atmosphere may have acted as a shield, which may have buried the impact cratering compared to today. Let's see here. And he has a complete list of the impacted Earth craters here. And let's see, did he have another chart here showing? It's like this is a possible chart of the Earth's atmosphere, and you can see that it's varied massively according to this chart here. So 150 million years ago, the atmosphere thickness in ATM is 450. That's 400 times thicker than what we currently have, right? That'd be Venus thick, really. So that seems kind of hard to believe all on its own. But that is what his paper is about. So if you are interested in that, then you can check that out. Now, like I said, Raymond, do you guys have any comments on that? Please let me know. Otherwise, I'll just continue rambling on. So, I think that maybe, Bill, you might have a comment on that because you think the dinosaurs got bigger because the Earth was smaller and has perhaps less gravity. But this is another way of putting it. You have extremely thick atmosphere allowing for the large dinosaurs.
Well, I would say that the U.S. Navy data, sonar data on the bottom of the oceans, showing the stretch marks for the expansion, three-dimensional expansion of the Earth, I think that is not refutable. It's so accurate, and it's we measure the expansion with our GPS devices. We can measure the expansion of the Earth along and perpendicular to the stretch marks. And that seems to be the only type of expansion that's occurring, and seems to be consistent with the data that we have. So
now, I was just at Yellowstone here, so I was wondering what you would think about the fact that we have these hot spots, like Hawaii is a hot spot, and Yellowstone is a hot spot. Now, that's basically showing that this hot spot, whatever the heck it is moving underneath the continental crust, because we can kind of track it over the past couple of million years. It just keeps on moving. Now, that would be evidence that the continent itself is definitely moving, well, assuming that the hot spot is at a constant spot there. But the thing is, if the Earth was just simply expanding out, then if we had any hot spot over any one given place over the continental crust, you'd think it'd just stay there, right? There's no reason for it to move, right? But
well, the crust of the Earth is at different thicknesses at different places, and so there are weaknesses in the crust, and there's the most of the activity, most of the earthquakes, and most of the volcanoes are along the current expansion lines. And,
yes, but it wouldn't matter. See, the hot spots are an anomaly to that whole thing.
No, they're all predictable. Geologists would tell you they're predictable, and
well, the thing is, I'm saying that if the Earth were just expanding, that hot spots would stay where they are, right? Because the continental crust is basically not really moving. In fact, everything is growing and it just expanding basically the ocean floor. The continents should remain basically motionless. But these hot spots, I would say, are contradictions to that theory.
Well, we
how do you explain the hot spots?
We had one of our members present a video he had made. He's a cartoonist. He does Superman and.
Yes, I've seen that, and that it nicely explains how all the continents move apart. But this would be a contradiction to that, saying that, well,
but that is based on data. Then his work is based on data. The other fellow's work is not so data dependent.
Well, it's not based on anybody's work. This is based on me going to Yellowstone and observing the obvious motion of the hot spots. But I suppose even in Neil Adams' video, he does show that the continents still are kind of moving around relative to each other. So I suppose he could probably explain it that way.
Well, but also within a continent you have motion, and like for instance, why is it that mountains are not uniform on the continents? It's because the continents are breaking up, and as they do the expansion, and so you find that most of the mountains are nearer the coastlines than they are in the center of the country.
Yes, so like I said, that could be a possibility that you just count the moving hotspot as being there is still some motion of the continental plates even within just an expanding Earth. I was kind of wondering if the expansion in Hawaii the same as the expansion in the middle of the United States. I think they're going in opposite directions though. So, but that is an area that you can investigate, I suppose. But these hotspots are anomalous, and they produce things like Yellowstone and all the and Old Faithful, which is still going, and things like that. Well, the one thing about Yellowstone is that you have the Yellowstone Grand Canyon of Yellowstone, which cuts down into the ground like 1,200 feet, but you don't see a lot more the thermal activities as you get closer to the bottom. So I was just thinking, although apparently there is activity, but it's mostly a big canyon with the water in the bottom. But I would have expected that you would have seen a lot more of those thermal features if you dug so far down in the ground. But apparently they only appear in just very, very, very specific spots in the park. So I'm just thinking that there just must have been some specific weakness in there that allows the heat to get all the way to the surface. And I also visited, say, a mine where they went down like 2,000 or 3,000 feet, and they were saying that at that depth, Your working temperature there is about 190 degrees. So definitely that's an example of the direct thermal effect, and that they had to have all kinds of special air conditioning in order to work down in those conditions. And then nowadays they show us the mine, which has been filled up with water all the way to about 100 feet. And now all you can see when you look down in the mine is just a pool of water, right? But I thought that was kind of interesting to go on the mine tour. But going on with the conference here, so Ray Gallucci, he actually analyzed the theories of one of our members, Duncan Shaw, as to the plausibility of his conception of gravity, which is due to a push force coming in from our heads. Now, his contribution to this is he's saying that the ether, whatever it is, that it comes down onto us like rain, and then when it goes into the earth, you know, one of the problems with Lesage's theory is that saying that the amount of heat that such impacts would create would instantly boil us and kill us with the radiant energy. But he's saying that what happens is that these things come down as rain, they hit the earth, become hot like steam, and then the steam rises back up into space, which then recondenses somewhere else and then rains down on other planets or other astronomical bodies. And that is how that would work. So Raymond, using his mathematical mind, went and tried to do some math around whether this would reproduce at least the 1 over r squared relationship that we observe between masses. And this would be due to shielding considerations still, that between two massless objects, we would expect to see a newer, of course. Let's see, we're getting an echo here. Everyone make sure to mute themselves if they're not speaking. And I believe his conclusion is that it would be consistent. So while no definitive conclusion regarding Shaw's ether concept of gravity can be drawn from this examination, is evident that at least mathematical constructs can be developed for 3 key aspects such as Shaw's theory. That Shaw's theory is plausible. That has been my only goal here, and further investigation into the physics involved hopefully will lead to greater insight into the potential validity of the theory. And then later on in the conference, actually before this, I think Duncan himself was able to give a presentation himself once again on his gravity theory. So we can discuss that later. But once again, Raymond doesn't have a dog in this fight, but he analyzes that. He also analyzed just the regular Sage pushing gravity. And once again, he's using a mathematical model to model just the shading effects that you would get. So he came and he drew up some pictures of what the shading would look like, and what the shading would be. Although I would think that this kind of analysis has been done before. So, what is his summary? He says, at least for a special case, large distances between spheres, a mathematical model of gravity that assumes gravity to be a pushing force with shadowing suggests a possible alignment with one of the known effects, namely that is an inverse proportional square to the distance. So this hopefully lends some credence to the theories first proposed by Fadio and Lesage, and since supported by many dissidents, physicists including and Schroeder, blah, blah, blah. Okay. So I guess this is very similar to his previous analysis on Shaw's thing. I mean, I don't think he's mostly just worked on the shadowing effects of the safe gravity. And really can't comment on, say, the particulars of like why that was ruled out. Me personally, my comment on this is I don't like shadowing type gravity. But I think what is essentially true, though, is that between, say, the Earth and the Moon, what's keeping them together is an actual push. That there are particles that are pushing, and one of the things that Duncan is saying is that anytime you have an attraction, like between a ping pong ball and a vacuum cleaner, that's not really an attraction, it's still a push. It's a push of the outside atmosphere causing it to go into the lower pressure area. So I think that is fundamentally true. That's what the pushing gravity people are fundamentally trying to find. But I don't think, my main criticism of these types of things is that in order for that particle to push, it has to travel all the way from its origin, which might be like the sun or whatnot, all the way across space and then hit the particle. So that physical particle has to go from point A all the way to point B. It's a long distance.
Can you mute Don's microphone?
Yeah, let's mute Don there. That it's just very difficult for any particle to physically travel that distance in space. It's like if you had an Olympic-sized swimming pool and you had a water hose and you stick the water hose in the pool and it's spitting out the water right there locally, but there's just no way it's going to make it all the way to the end of the Olympic pool in any detectable way. Because if you're a particle and you have to go through a sea of particles that are all going in random directions, that's going to eventually stop you, and it's actually stop you fairly quickly. It'd be something like a 1/r^cubed or maybe 1/r⁴ power. It would just drop off extremely rapidly. So I just don't think that it's possible for these particles, which are supposedly impinging on you, to travel very far before it gets completely randomized, right? And then once you get into a completely randomized situation, then it's kind of hard to see that you're going to generate any kind of net force. So this is why I think it's probably, my own personal opinion, is that gravity must be some kind of a wave phenomenon. And waves can travel a very, very long distance. So if I put a speaker at the end of my Olympic swimming pool and I turned it on, you could hear that easily all the way on the other side. You could easily detect that and recover the signal that was being transmitted with very high fidelity, versus trying to detect water coming out of a hose. You would never detect that at the other side. You probably couldn't tell. There's probably nothing you could measure to detect that those incoming particles. It just cannot travel that far. But a wave does travel, and so the question is, if there's some particles pushing, then it may be due to the action of the local particles pushing, because I believe that there may be local, if you can have any kind of pushing, that must be from the local particles. And the only way the local particles can be pushing is if they are being moved back and forth in a wave fashion. So then it would just be a question of how is it you can get less pushing between the Earth and the Sun versus outside the Earth and the Sun, or the Earth and the Moon. So that's how I would kind of relate that. It's like, I think the basic concept is probably true, that gravity is due to some things pushing upon our bodies, and that there's just less pushing from beneath, so there is a net force going downwards. So it's not like gravity is always all pulling. I think it's always a tug of war between different forces, and when there's more forces this way than there is that way, then we tend to be going that way. So, and in my conception of gravity, the gravity is just due to asymmetric electric field, that the Earth is a positively charged, and that causes all neutral matter to be attracted to that charge. And then you have to motivate the electric field, the electric charge itself, as being motivated by these waves. And the idea, I just seen a video by Jeff Yee, and he kind of explained the same way I do, which is that between, say, two positive charges, you get a constructive interference, and that creates high pressure, versus a positive and a negative. That creates, between the two, destructive interference, and then that causes a lower pressure. So once again, the real only reasons why particles come together is because they're being pressed on the outside more than they are being pressed on the inside. So in the case of gravity, we have a situation where our dipoles are aligned to the Earth. I guess that would be a direct prediction of say, my gravity theory, which is electrically motivated, that we should be able to measure the dipole orientation in every single speck of matter on the Earth. And generally speaking, if we could do that, you would see it pointing downward, because the electric charge causes your dipoles to align in a specific direction, and then the tiny difference between the positive and negative charge of that dipole creates slightly stronger pull. And it isn't much, but added over the surface of the Earth ends up being quite a bit. But that would be kind of along the lines of the pushing gravity, except that you'd be pushed by local particles, not particles coming in from outer space. Now, so that was Ray Gallucci's contribution to the conference. And one of the more interesting contributions was this from Sandero Guerrera, who has this mirror model. And, we all know that, the human body is mirrored from left to right. We have that kind of symmetry. But he's saying that there's another symmetry between your head and the rest of your body. And he started out by saying that, like your eyeball sockets, those kind of look like the holes, the sockets that are in your hips. So he's saying that it's kind of a reflection that anything that you can find in your lower body can in fact be found in your head. So, you could say that, your mouth is kind of like the opposite of your butt and things like that. And so that seems a little bit far-fetched, or things like your brain is reflected in your intestines or your colon. But he does have some interesting factoids. Like he's saying, the liver is like related to, say, the ear, and he pointed out that there's some genetic mutations that cause a mutation in the kidneys, but they also cause mutation in the ear. So he's saying that there's some kind of direct connection between the creation of those two elements in your body, that somehow the head reflects those other places in your body during like embryo growth, because we're showing there's just when you first start out as an embryo, it's very simple. There are only like three pieces that start out, and each piece ends up being a different part of your system. So he's saying things like, say, your teeth are related to, say, your nails on your fingers, right? And let's see here. One of the other interesting things that he mentioned is he says, like, your nose is opposite to your sexual organs. And he was saying that they did some experiments on rats where they did something to their nose, and they effectively changed their gender preferences. So indicating that it has something to do with something in your nose, right? You wouldn't think it would. But he's saying that these things are directly reflected in each other. Let's see here. So what does he say here? So you have genetic experiments. So his note to the reader here is that this has been a brief text considering the complexity and depth of the subject. Certainly much more can be said about specific aspects of the model. I'm aware that not all the organs of the body have been addressed, and that this is alleged mirror effect can have apparent variations among different species and even different kingdoms. However, I hope the reader has been able to grasp the significance of the evidence that has been put forward despite the unconventional nature of the hypothesis. So I guess that's something to think about. So I asked him about, what exactly are the practical practical applications of this, To which he answered to the guy who was trying to figure out what good is electricity, right? Which at which point he said, I don't know, but I know you'll figure out a way to tax it in the future, right? Okay. But I thought that was kind of an interesting thing. So for my part in the conference, I was leading a conversation on how the electric and the magnetic field works. So David had motivated that as a organization, we should come up with like the list of standards of things that a theory should try to explain. So for electrostatic field, we should have a list of, 10 things that your theory must be able to explain in order to qualify as a good model, right? So I did go through a lot of Bob DeHilster. So we mentioned the G1 gravity. So I think he was the only one in the room who raised his hand and said that I have an explanation for how the electrostatic field works. So we made our little list of things that we thought that we would think a good theory should explain, and then we went and explored each of those points with the various different theories. So basically, only two theories were presented. Just the G1 theory, although I believe that basically that the attraction for them is inherent or fundamental property. That doesn't, that is just fundamental. So if you make things fundamental like that, then you don't have to answer those particular questions. But we went and did that. I presented my own idea about how the electrostatic field works. As we discussed earlier, you could think that the electrostatic field itself was fundamental. I personally do not. So my preferred embodiment of this whole universe thing is to say that the world is filled with the particles of electrons and positrons. And once you start with that, then you have at least a medium which is neutrally charged. So basically, I've been leaning towards describing this as basically a sea of neutrons, since I believe that neutrons are also just positrons and electrons, just a dipole pair, and people recognize the existence of a neutron. If you tell them it's a positron electron, then they'll go, oh, well, those annihilate, and that can't possibly exist. But we know neutrons exist, so if you just had a big sea of those things, I think that would account for most of the properties. It would be accounting for a basic medium for compression and rarefication waves, and those could serve as the electromagnetic wave. And then I have to then motivate why an electron and a positron should attract, and like I explained before, that between a positron and electron, they create some kind of interference, some kind of destructive interference between them. And but if you have two of the same kind, then that always creates a constructive interference. And it wouldn't matter which one you had, whether it was positive or negative, both of those would create constructive interferences. And if you had the opposites of them, those would always create destructive interference. So, because it's really hard to explain, like some of the other models which say that the electric field is like something which is spewing out some kind of particle, and then the electron is like eating all the particles. But the problem with that is that then you would only get two electrons being attracted, trying to eat the same material, or the protons. But that would be wrong. Electrons would repel each other, but according to that model, they would attract each other. And there wouldn't really be any reason for why an electron should attract a proton, because this thing would be spitting out as much as this thing is eating. So they would be perfectly happy being still. And then, but you would get that two protons would be repelling each other. So that's really the only thing that actually works in that. And those kinds of things, that it's very difficult to get this opposites attract only kind of reaction. And the only thing that I know that does that are these kind of constructive or destructive interference. So I'm convinced that there must be space filled with the neutral particles, and that there are waves that go through those neutral particles, and those react constructively or destructively between the charges to create what we feel is the electrostatic field. And I think that since the electrostatic field is just a wave, it's just an ordinary electromagnetic field wave, then what we feel as what is the field is just the actions, just the range of these waves. They would be going out in spherical waves away from the electron, and that's what we measure with our meters, so that we measure the strength of that particular frequency of wave that's coming off the charges. So what is charge? It's electromagnetic field coming off of a positron or electron. This is how I explained it. And then I went down to one of the things that you need to explain in any electromagnetic field theory is its relationship to the magnetic field. And so there I explained the magnetic field as just being a polarization. If I have dipoles, then I say, well, those can be pointed in one direction, so that can represent at least the directionality of the magnetic field. And the number of dipoles you have, which are all pointed in the same direction, can represent a magnitude. So physically, at least, the magnetic field can be represented by at least dipoles. Of course, dipoles are very much like magnets, right? You have two opposite sides, and you get enough opposite. If you play around those things, they act basically just like magnets, right? So the only question is like, what causes electrons to deflect in a magnetic field? Because this is the one thing that the magnetic field does. So if I get a magnet, I shoot an electron next to it, it will curve, right? Versus if I take away the magnet, it goes straight. So the way I explain that, at least in my theory, is that if you have all these dipoles and they're all pointed in the same direction, so you have like a plus on one side and negative on the other side. So when you shoot an electron between them, then it sees the positive side on one side and negative side on the other, and it will be preferentially deflected. Preferentially verge towards the opposite charge. And if you have a bunch of these dipoles all lined up in the same direction, it will go and curve even more. So that explains fundamentally why is it when you shoot an electron through a magnetic field, it sees this aligned dipole field and it wants to go towards basically the positive poles that it sees as it's going by. So that fundamentally is what causes the electron to turn in the field. So what is the magnetic field? The magnetic field is just the aligned dipoles in space. You have these like neutrino C made of positron-electron dipoles, and the magnetic field is wherever you see those dipoles aligned. Because normally with no magnetic fields, all of these dipoles will be randomly arranged. But within an aligned dipole, that's where we see a magnetic field, and that's where we see the deflection of electrons. Now, the other thing you have to explain about the magnetic field is why do they exist in the first place? And they only seem to exist in the presence of moving charges. And so I explained that if you have these moving charges going through space, it's kind of like a wind. And these dipoles are kind of like flags. And if you push a wind through a set of flags, they will all start pointing in the same direction. So that's kind of an analogy, and I'm not sure that's a really great analogy, but and I'm not exactly sure how that works with real charges. But that's kind of what I'm pushing for, that the reason why you have to have the moving charges is because it creates effectively a wind which causes an alignment, and then that alignment will cause a deflection of the charges. So, but definitely in any place you have magnetic charges, magnetic fields, that does indicate the presence of moving electric charges, even in permanent magnets. So if you have your permanent magnet you've got attached to the fridge, something about them must have a permanent moving electrical charge. So in some ways I've speculated that ferromagnetic materials permanent ferromagnetic materials are actually, in a way, a room temperature superconductor, because there has to be a non-stopping superconducting loop in there in order to create the required currents for the magnetic field. And then finally, I had to motivate what is that force that you feel. So you get two permanent magnets, you put them together, there's definitely either a repelling force or an attractive force. And so what you're feeling there is that you've got these magnetic loops going in the material, and they're made out of electrons, and you're immersing those electrons in this field coming from the other magnet. And that's going to cause the electrons in this magnet to deflect, either towards the other magnet or away from the other magnet. So you have all these electrons here, but they're stuck in the material. And one of the interesting properties of the best magnets is that they're ceramic and they're non-conducting. Which means that if you have your superconducting loop, those electrons are trapped in there. They cannot move to the surface, for example. And what they do is that since they can't escape, they actually drag the bulk of the material with them. So if you got the electrons in here and they're wanting to go this way, it's going to literally drag the magnet in that physical direction. So that is what you're feeling. So you imagine with just millions of electrons all trying to go towards each other and pushing the bulk of material together. So you're feeling the effect of millions or billions of electrons trying to be deflected into the direction of the other magnet. So that's what I explained, what you're feeling as the magnetic field. So that was my contribution to the conference. I did it completely old style and did it with whiteboard and no slides, no PowerPoint, just an open discussion kind of thing, just like we have here during the Saturday mornings. And incidentally, I did win an award, which was where's my award? Which was a leadership award for hosting these Saturday chats. So I appreciated that. So let's see, going on here. So we had a presentation by Jim Marson. See, Jim is here today, and he presented his proposed experiment to put a low orbiting satellite with the Michelson-Morley experiment on board. So the idea here is that on the Earth, we do the Michelson-Morley experiment, and well, we don't detect anything really. Not much to detect. But he's saying that if we were to go ahead and put this in low Earth orbit, then we should be able to then detect the speed of the satellite. Because basically we're not detecting anything on the Earth because we're basically kind of like fixed in our own ether bubble or our shell, so we're never really ever going to be able to measure that. But if you put one out into space, then we should be able to detect the speed of the satellite going around the Earth. And so this is a low Earth orbiting experiment, since that is presumably less expensive to do. And there's always lots of spacecraft going up into space. And we should then be able to overturn the tyranny of Einstein's relativity by showing that, I guess Einstein's relativity would probably say that you should get zero out in orbit as well, but then that would be kind of hard to explain if it didn't. So I think that was the gist of it, right? Is that right, Jim? And Jim came and presented to the conference remotely. We're having some challenges with our internet, but I think eventually we got it done.
Was there a recording made? It looks like the one that's on the website is only about 5 minutes. It cuts off after 5 minutes. Is there a...
Yeah, like I was saying, there were some significant challenges with our live, at least our live presentation. Now, I haven't checked to see on the YouTube whether we posted all of the presentations there. Let's see, I think,
Was there a fuse recording maybe that was longer?
yeah, there may be a fuse recording, but it should have also been recorded to the SD card to our Sling Studio card. So hopefully we do have the recording. I haven't had a chance. I think I just got back from my vacation yesterday. I have not been able to check back, but definitely we lost the Facebook Live feed. Like shortly after we started there. Now I remember I did get a fuse recording we had a presentation by you and Roger, and I know that we recorded one of them, but not the other one. So I still have.
It looks like Roger's got the.
Yeah, I think Roger's got. Okay, well, like I said, I haven't been able to check. Hopefully, we recorded it somewhere. And it does take some time for us to digest all this stuff. It's a very long process to upload things to YouTube. This is not something.
Hey, you guys did a great job,
But hopefully we did that. But so did I get your summarize your talk there? Okay.
Sorry.
When did I summarize your talk? Okay. You're making any comments about your proposal to put a Michelson Morley experiment.
Well, the other thing I'd mention is that the SAGNAT correction for the GPS really is the clearest hint that there is the Earth does rotate within the ether sphere that surrounds it, so that the velocity of the ether at the Earth's surface is just due to the Earth's rotation, and that's too small for Michelson-Morley type experiments to be done to unambiguously detect it on the surface of the Earth. So,
well, I guess my question would be that the GPS itself already. I think I need to mute you here because you're going to have feedback here. That the GPS itself has always kind of disproved relatively, and like the MMX effect itself, by showing that the frame of reference that you have to use is the Earth-centered inertial frame, and that alone should show the effects that you're looking for here, that you can detect the speed of the satellites. So it's like we can detect the speed of the GPS satellites, assuming the Earth is the center of the frame. And we have to make compensations for those velocities depending on which direction they're going. If they're heading east to west versus west to east, you have to add and subtract the velocities right there in order to make it so that all of these clocks are synchronized. I'm not 100% sure about that, but I guess my point would be that there's probably already plenty of evidence that things like the speed of light is constant in all frames is a bunch of baloney. Although I believe that Einstein never actually said anything close to that. And that has just been one of the other papers that were presented was that Einstein has been mistranslated. But during the paper, I didn't see any super serious mistranslations, as the word speed and velocity could get confused in translations. But I don't think that would necessarily make a big difference versus the kinds of things that we as dissidents are looking at. We're looking to disprove the postulate that the speed of light is constant in all frames of reference. And it's well, duh. But Einstein never said anything close to that. He says that the speed of light does not depend upon the speed of the transmitter. This is effectively what he said. Didn't say anything about speed of light is constant in all frames. Didn't even come close to saying that. And no translation of the German will get you to what the dissidents are saying that postulate says. So Michael, you raised your flag?
Well, in my ether model, the ether has its own dynamic, which is which is vibratory, and they interact. Elemental ether particles units interact with each other, and so the ether would not be fully inertial with respect to the conditions of the Michelson-Morley experiment. So it's just irrelevant. I mean, the whole Michelson-Morley approach to trying to find an ether, detect an ether, is not valid because of the nature of the ether itself, which they assume that the ether is fully inertial with respect to the conditions of the Michelson-Morley measurements. But the ether has its own dynamic, which is different from, it's separate from the dynamics of the Michelson-Morley experiment.
All right, so maybe it doesn't count. Although I think probably the main problem is that even if it was privately funded, even if we did do it, even if it did show what we're looking for, that it would still be pretty much ignored. Just like the Signac effect is currently ignored. So,
well, the difference is that the Michelson-Morley experiment is a second-order experiment, and that's the one that relativity is based on, whereas Sagnac effect is a first-order phenomenon in V over C.
All right. Well, but moving on, we had another speaker, Cameron. Now, since I had to typically leave early during the conference, I didn't actually hear his presentations, but he presented two things. One was reason for a cyclone to spin. So Coriolis force only terminates. I believe he's trying to motivate the fact that the Coriolis force is generally credited towards creating these things, but he's saying no, there must be some other force. And I guess I could kind of agree with that the Coriolis force generally is only involved in, say, controlling the direction of the spin, but there's got to be some other major forces that are causing the actual cyclone to spin and to have so much energy as to cause the gigantic hurricane. So, and I think most people do recognize that's true. I mean, mostly the hurricane is due to the ocean heating and evaporation and creating pressures, differential wind pressures. And I'm not a meteorologist, and I don't even play one on TV, so I don't pretend to know how those things work. But that the only thing that the Coriolis effect is adding to is, I guess he says that it only basically terminates it. I'm not exactly sure what he means by terminates it, but certainly it controls its general direction, and that's pretty much all it would do. That was one of his papers. And the second paper that he had was something that said that the universe is infinite, is ironclad. So he's very much a advocate that the universe must be infinite, right? So he comes up with some observations like we've never observed the edge of the universe. As far as we can see, you can look in the darkest place in the sky and just see nothing but more galaxies and more galaxies. Yeah, so we have never found an edge. Then he say things like we observe things like accelerated expansion, but that doesn't seem to make much sense. We don't see any huge voids anywhere, I suppose. I guess that would be more along finding the edge of the universe. And let's see here. A lot of this has to do with the edge of the universe. But in any case, he had like 6 or 7 reasons for saying that the universe must be infinite, and he had a number of arguments against Big Bang Theory. Like my comment would be is that it doesn't matter, right? Because all we really know is the universe that we can currently observe, and whether it's been here forever or came from a Big Bang or not. I guess I was asked that question. He was trying to nail down whether I believed in Big Bang Theory, And my response has always been, I was not there during the time. I can neither confirm nor deny the existence of a Big Bang, although my personal preference is for a eternal universe, that it's always been here. And I figured that if it ever like ran out, it would have done so already, right? But it hasn't, and it appears that experimentally we can't find the edge, and it doesn't really look like we can find a center. So I would be more in favor of a steady state cosmology versus a Big Bang cosmology, since I'm not terribly convinced about the whole redshift thing. We seem to have all these objects going everywhere. And let's see here. So I've already explained Duncan Shaw's conception of gravity and what my thoughts were on that. So I guess that takes us to the end of this 2 hours reviewing what's going on with the CNPS Conference 2019. So, you know, it was a fairly small conference. There are about maybe a core group of maybe 15 of us there, but it was very intimate, and you know, you would go to lunch and you would get to talk with people in a very detailed fashion. And so there are some advantages with having a small conference, but I would encourage anyone else who would like to go to a conference to please attend. So this year we were at the West Coast, and next year we'll be on the East Coast. So for those of you on the East Coast, that would probably be a better opportunity for you to participate. Now, hopefully, currently we have all of these presentations, except for the ones that get cut off due to challenges with the internet, with our remote ones. Those are all on our Facebook page. We've transmitted all those live, and at some point, we will go and put all of those presentations on YouTube. Like I said, it's quite a bit of manual work to get those things transferred over, and it's a lot of bandwidth. And hopefully we will do that. And Jim, I'll go see if I can specifically find your presentation. Hopefully we recorded that one with Fuse. But that will do it for this week's Science Chat. So hopefully see you next week.